high school.
Hmm.
I'm trying to.
Okay, email.
So either so like on days like today, I have to hang out around here, which I mean his brother and sister. um, I have to. I don't. And I don't swear this. So sometimes I hang out with my friends out because I'm not going to drive to Fremont and then have to drive back. Otherwise, I was like walking or something. Second for me.
Okay, so this is what we bought, and these are little relays that you can use, and they're packaged right there in front of you. So you can use them as you see fit, because I think we're going to run out of relays if we don't. So this is I looked for all the different types of relays I could get, 24 volts, and you can take half of one of each of those boxes or more if you really need them. But I got 6 boxes and there's 10 in each. That's 60 more relays. So have at it. There they are. And I'll put them up in the, I can take them up and put them in the room upstairs, or you can deal with them as you see fit. Okay? They only have one contact on them. They only have one normally open, normally closed pair contact on them. But that should be enough for most of the applications. You only need you only need one contact in certain cases. You need two in other cases. So for the ones you need one, use this one. For the ones you need two, use the others. So that gives you an overabundance of relays. So I got 10 times 6 is 60 more relays. Okay? Any question about that? Has anybody started getting their project put together yet? Did you run out of relays? No? You didn't run out of relays?
We just kind of started. We just sort of did the steps.
Yeah, yeah, yeah. Has anybody put the limit switches on yet and tested that part of it out or anything? You have? Good, good.
To see if we can get some to move so the air won't be soldered.
Okay. You had a switch to the circuit yet? No, nobody's added a switch to it. You don't have to. It's up to you. Okay, when we get closer, I'll show you how to do the PLC part of it so that you are prepared for that as well. So this is 3 labs and then 1 lab. 3 labs for the relay part and 1 lab for the PLC part. And it's 4 labs, and it'll cover you the rest of the way. Okay. I'll be around. I'm not going to, like I said, I'm not going to hover over you, but I will be around and help you. At least some. Okay, I'll be there during labs for a while and go in and out or whatever. And oh, this is the fun part, because this is a little bit more than what you've done before. This is kind of a real project, and it takes dedication to get it done because there's a lot of wires. And you'll get it. You'll get it. You might blow something up in the process, but you'll get it. You might see smoke. You'll get it. Questions. So I got 60 more. And you say, well, who paid for that at the university? Your lab fees paid for this, so this is good. We'll get through that. Any questions so far? Any questions in general? Are you all comfortable with the Bodie plots? Anybody have any questions about Mr. Bodie or Miss? We had a Mrs. Bodie as a teacher here, so I have to always say, "Are you comfortable with Miss Bodie?" No. No. Did anybody have any? Everybody understands perfectly how to do those 8 problems. You got them? No problem. Piece of cake, right? Good. Well, we're moving on. So, what's next? He asked. Well, we ran out of material. We ran out of the end of the book. What do you do when you run out of the end of the book? You go to the next book. And the next book, the next book. So the next book in your sequence is the electronics book. And if you weren't interested yet, you will get interested because this is what's left. Semiconductor devices, and then we get into op-amps, the last book. So there's two more books, and I don't know how far we're going to get in this book. The the problem is I haven't taught this stuff in quite a while, and we've been through. But this is the next book in the sequence. And I'll put this on your website so you'll have it. And this will be, I'll be your teacher for, at least it's planned I'll be your teacher for 2010. You got me again, I'm sorry to tell you that, but now we've had to readjust and readjust and readjust and readjust. But I taught this course over the years, for a lot of years. I'm not a semiconductor, or I'm not an electronics person as far as where did my interest lie? I could do this stuff and I was okay at it, but don't depend on me to build you a circuit that will go to the moon or something like that. I'll figure it out eventually and I'll get something that'll work, and I will help do stuff like this, but my main goal or my main interest always was with the controls part of it, which basically went around this part and kind of said, we're going to take the end results of what somebody built and we're going to use it to make something happen. Okay, so I, for what it's worth, have always gone that direction. And if I could buy something, I didn't make it. If I could put something together that was somebody else's, I always found that advantageous over building it myself and putting it in a control panel or something like that. Some people went the other way, and I always tried to find something that I could buy from somebody that I could modify or augment that would do the same thing. Because why? First of all, it's easier. And second of all, if you open a control panel and you see a board on there that is wired by somebody other than some professional, you see it with wires hanging out, all that kind of stuff, you're going to always point to that as the problem. If it is or isn't, it's always going to be the problem. So if you have to, you do that, but only as a last resort. That doesn't mean that you don't have to do that from time to time. It doesn't mean you don't have to come up with ways of tricking things to make it work according to what you want it to work as. But if you can get around it, by all means do. Okay? Put a standard part in there, program it, do whatever you have to do, do whatever you have to do in order to make it look like a standard part, even though you've tricked it into doing something that's not. That wasn't its original purpose, but you tricked it in order to make something happen like what you wanted to have happen. Okay? That's an easy way of saying don't reinvent the wheel. And if you don't think that's important, Owens Corning, who I used to work for, basically had a group in Granville, Ohio, at their Research and Development Center, their R&D center, that the head of the group came in at one of their big meetings and basically threw a microprocessor chip down and said, "That's the future, boys." And everybody looked at him and thought, what are you doing? What are you talking about? And because nobody had a 16-bit PID controller, they only had 14-bit PID controllers, we were going to make our own, and we were going to be more accurate than anybody else. And he didn't look at the physics of thermocouples, because thermocouples, when they transfer a value, they jump by about a degree of Fahrenheit of temperature. In other words, it's just in millivolts, but they're here, and then they jump to a value here, and that jump is always a 1 degree or more. And yet he wanted to control to a tenth of a degree Fahrenheit. 2 to the 16th is 1 over 30, what is it? 32,767, which is less than a tenth at 2,000 degrees, okay? So he wanted to control to a tenth of a degree Fahrenheit, and all the others controlled to about a half a degree Fahrenheit. And he thought he was better. But the half a degree Fahrenheit was still better than anything that we would ever have need for, because when it jumped by a degree. And he was trying to invent something that didn't need to be invented. So anyway, long story short. And they all got canned eventually. The whole project, everything disappeared, but they had spent an inordinate amount of money in the process. Crazy world. We are going to do it ourselves. We're going to invent it ourselves. Usually somebody has a product out there that will do it for you and do it better than what you can do it yourself. But that being said, you might find yourselves in a position where you're actually doing something, creating something from scratch that has never been done before, and you have to depend on what we're studying now. Okay? So you have to come in and you have to put a circuit together that'll do exactly what you need, and nobody else has one like it. So that is the rub of what you're going to get today and for the next few weeks, as opposed to, is this something that you need? Yes, because you need to understand how they work. Is it something that you might actually put together and make work in a factory? Don't know. But you might. You're always having to think that way, but don't automatically think that way. Don't think that because I know how to put a circuit board together that does all this neat stuff, that's the way that I should go. Because usually it's a trap. Any questions on that comment? That's an editorial comment starting a whole book that says, you might need to know this. You'll definitely need to know it occasionally, but don't plan on building circuits on a board, because most of the time you don't need to. But occasionally you do, or occasionally you need to troubleshoot something and you need to understand the concepts of what are going on here. So let's just look at what this book is about, first of all. So we start with introductions, of course. Start with a nice, pretty picture. It's a free book, but it looks and acts very similar to the other books that are out there. So Fiore does an excellent job of mimicking, if you want to call it, the Pearson, Prentice Hall, the best books that are out there. So he basically takes what they have and mimics it very, 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 very well. And he adds his own touches in some places, which I appreciate. I'm all for free books. And I'm all for doing stuff with a free book. But you can buy the books that are the best that are out there. The Floyd series is probably the best series of books like this. It costs you $230 a piece. Okay? So you can have the Floyd book, and you can have a copy on your shelf, nice copy and all that good stuff, or you can have the Fiore book for free. And I'm all for free. I'm all for free. And they're the same book. Except that the name on the front of it doesn't say Floyd, it says Fiore. But that being said, that's kind of the introduction to this whole book and this next book. Now, I don't know how Tony introduced the first book to you, the DC book, and then I got into the DC and then the AC book. But this is a new area. And this is semiconductor devices. These are nonlinear devices. These have peculiarities to them that allow you to do things that you couldn't do before. Now, up until now, everything went downhill. You started with a voltage up here, and then down here to the right, you got less and 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 less, right? Now, get over it, because now you can go like this. You can do all kinds of stuff. You can go from a low voltage to a high voltage. You can flip things around. You can do all kinds of stuff. Okay, so this is totally a different mindset than before. Everything was linear before. Now things are not linear. They're not linear, and they do things differently in different areas than they do in other areas. So what does that mean? Well, if you go in the forward direction and you go in the reverse direction, does it do the same basic thing? Is it on a line? And these aren't, okay? They're very different. They do some very interesting things, and they'll give you amplification that you wouldn't believe otherwise. And I go back to my when I was in high school, and it was the thing in high school when I was growing up to have a 5 or 6 transistor radio, okay? Because to have a 5 or 6 transistor radio that you could take around with you that had a battery in it, that you could take around and listen like this, was the coolest thing people could do. They could walk around and listen to their tunes from their local radio station on their 5 transistor, 6 transistor, 8 transistor, oh my goodness, radio. That was the mid 1960s, okay? I graduated from high school in 1967. But then in the 1960s, if you could carry around a radio and be listening to the tunes, that was cool. That was you were in, whatever. Now that dates me, of course, and you think I'm an old guy and very old, and maybe in a way I am, but this stuff is not that old. This is not things that came about that they're digging up from the Pompeii ruins. They didn't dig up any 5-volt or 5 transistor radios. They did not dig them up because they weren't around. These things came around in the late 40s, early 50s, and by the mid 60s, they were a hot item. And then they figured out how to put all this stuff together and make it into one big, massive chip, and they did. And now you got all kinds of stuff, and it's all done, on pre-manufactured boards and someplace else, and we don't get to touch that. Which is a shame, because we should be able to touch that stuff. We should be able to build things ourselves. That's why this project that you're doing is so important, because you get to see some of the evolutionary process of how to build stuff and how they did it before 1980 or 1970, and now how we're doing it now in the factory. And then also this course and the next course shows you how to build the stuff that goes on a board that you could put in a TV or put in a computer, whatever. And these transistors are the building block of everything else that you do. So they're in this book. Talk about it. BJTs, bipolar junction transistors, or FETs, field effect transistors. And again, we're going to get into the nitty-gritty of that. Maybe we're not going to get it all the semester. We're going to get into it a little bit. We're not going to go very far, but we're going to get a start on this book. And then we'll pick this book up next semester and finish this book. And then the following semester, you can take on op amps in their entirety, and you can have that as a whole course. Okay? Or you can finish this book and then go into op amps. I don't know. I'm not prognosticating exactly. Now, in the day when we were teaching this with the Floyd book, this book was 2 semesters long. Okay? And it included the op amps. So the Floyd book included this book and the succeeding book, which is his op amps book. You say, what are op amps? You can wait a little bit, and we'll talk about those in a little bit. We got enough to talk about now with this stuff here. So basically, we are into small signal type devices, and at the end of this, they talk about power devices and IGBTs, isolated gate bipolar transistors. So this is the big boy stuff that transmits a lot of power and we talk about them at the very end of this book. IGBTs are power switching transistors. A lot of current, heavy duty, all that kind of stuff. And then another chapter on Bode plots. Oh my goodness. So you'll get Ms. Bode again in frequency limits. We'll talk about that a little bit. I don't know if I'm going to end up teaching this course next semester or not. I'm not wishing that I don't, and I'm not wishing that I would. I just don't know. Okay, so we get into the basics of semiconductors. What are they? Well, they're on either silicon or germanium, and they started out with more with germanium, and then they ended up more with silicon. But basically, I don't know for sure whether they're going back to germanium a little bit or not, but basically everything is on silicon. And what are we talking about? We're talking about things that are semi-good conductors. They're not excellent conductors, and they're not insulators. They're semi in the middle, okay? And the first transistor was invented at the Bell Labs in 1947 by John Bardeen, Walter Brattain, and William Shockley. All right? John Bardeen was a physicist who did everything theoretically. He presented things on paper, and then he built them. He did that through his whole life. An aside about John Bardeen, he was at Bell Labs, and then he went to the University of Illinois. He worked in the physics department of the University of Illinois. He never lectured. Anybody know why? Anybody have a thought on why he would never lecture? He had a profound stutter. He's a brilliant man who had a profound stutter. He never lectured. But one guy that I knew was one of his students, graduate students. One guy that I knew, I was the roommate of the brother of one of the students of John Bardeen. Okay, how's that? And he would come in, and Jerry Johnson was his name. He'd come in and talk about his talks with John Bardeen. And he just shook his head every time he did, because this guy was way ahead of him in everything he did. John Bardeen was way ahead of him. Jerry Johnson went ahead and got his PhD in physics. I don't know what he did with it. I have no clue. But John Bardeen was a brilliant physicist. He did everything with math, and then did it in the real world. So John Bardeen invented the transistor on paper before these two guys went ahead and built it. That's how this went. That's how this rolled. This guy did it on paper, and then these guys put it into practice. Shockley especially he actually built it, but it wouldn't never happen had John Bardeen not done it in theory. So if you want to know how some things are invented, not all things are invented by just looking at it and doing something in the laboratory. Some things are invented on paper and then put into practice, and that's what John Bardeen did. Okay? So anyway, two guys, John Bardeen and, now I'm embarrassing myself because I don't remember his name, but John Bardeen and then the other guy that invented the LED were at the University of Illinois when I was there. But I saw the one guy, but I never saw John Bardeen. But the other guy was, think of his name after I leave today, but anyway, he was Nick Holonyak. So the two that I was there at the same time that they were there, but I never met them because I was just a low-life grunt, freshman, sophomore, junior, senior in electrical engineering. But they were there. Okay, so John Bardeen, Nick Holonyak. I think it's a Y, Holonyak. This guy invented the transistor. This guy invented the LED. And another guy that was there and had graduated, is not a graduate, and everybody talked about him, was the guy that did the integrated circuit. Now, I don't know what they're still doing. I don't really care what they're still doing. I don't belong to the alumni association. I'm not a big whatever, but I still root for the sports teams. But anyway, this guy's name after a while too. But anyway, these are the big guys, the big guns that everybody made big deal about. And I guess I should too. But if you talk about these guys, they were just people. Nikolyak was the son of a Russian immigrant that went to Southern Illinois to mine coal because they did strip mining, and he was he knew how to strip mine. So they did strip mining in Southern Illinois back in the 30s and 40s, and his dad was a strip miner. So anyway, so this is kind of the basics for getting started. Is just basically, and they do some things here. They say now in general, you're going to be dealing with DC and AC. All right. So if DC, it's a capital letters, and I'll try my best to accommodate that. This is small letters. Okay. That's what he basically tries to do. Is if it's DC, it's capital letters. If it's small letters, it's AC. Because you're going to mix the two. Okay. So here's an atom. Okay. So we start with atoms. We start with the Bohr model of an atom. And we start down through this and we say, now, how many electrons are there in the outer shell? In a semiconductor, there are 4, which is half of an 8. Because in the shell underneath it, there were 8. 1, 2, 3, 4, 5, 6, 7, 8, right? So in this outer shell, it's halfway there to another standard shell. We're right in the middle, which gives us the ability to either add 1 or subtract 1. Here's an electron. Give me an electron. I can hand them back and forth. They can play nice with their neighbors and hand back and forth electrons. Okay? So in this outer layer, there's 4. So there is an energy level associated with each of these, and that energy level, as it goes higher, as you go out to the outer layer, you have to have more energy out there. So there's more energy involved with these guys spinning in the outer layer. Now, and in its crystalline form, silicon is very, very orderly. Now, this picture is a two-dimensional picture of something that's 3D, and here's the 3D model of it. Okay, so in the 3D model, you can actually see how it looks with these crystalline structures kind of sitting there all holding together in 3D. So this is the picture of what actually is going on inside the crystalline structure. They're sitting there, they're all being held together by sharing of electrons with other atoms. Notice I'm not dwelling on this because it helps you to understand that there is an order to this. But we're not going to have a test question on this. And if you can understand the 3D model, this one right here, you understand that there's an order. This is a nice picture, but it's not real. This is a more real picture of what's going on because everything is in 3D. Okay? And also, if you add an electron or subtract an electron, they can travel through this whole thing pretty easily. Now, how do you add or subtract? Dope it. Sounds ridiculous, isn't it? But you add. So how do you do that? Well, you let some other material seep in, all right? And it can either be a lot or little. So you can have silicon, and then you can actually add to it some 5 atoms. And in order to do that, you have to expose it to something that has 5 atoms. And that's called doping. And that gives you an N-type material. So if you have silicon as a base, okay, here's a slab of silicon, and I expose it to something with 5 atoms in that outer shell, that puts this area of that shell. Let's say we tape off all the way over here, we tape off all the way over here, and we just let it expose to this little piece right here. What does that do? That allows this 5 electron stuff to creep in and stay and set in here, okay? So it kind of oozes in. It's called doping. All right? Now, one of the dirty parts of all this stuff with 5 and 3 is one of the 5s is arsenic. So, how many of you like to handle arsenic? Not really? Not today? No, it's dirty stuff. But anyway, there's some 3 stuff as well, and you can dope with 3 stuff. Well, if you dope with 3 stuff, what are you doing? You're creating a p doped area, positive doped area, which p means lack of electrons, okay? N means excess electrons. So you can get straight old semiconductor material, you can get a p doped area, and you can get an N doped area, all right? So if you put these together, what do you get? You get diodes, you get transistors, you get all kinds of stuff. Okay? That's how it works. In a similar manner, we introduce a trivalent impurity. Our crystal model now features a hole and a location where an electron is lacking. And for this reason, trivalent impurities are sometimes called acceptors. The resulting picture is right here, where you have some with holes. If there's +3, that's a missing electron. That guy right there is missing. So that's a p-type material. Okay? You can have n-type, where there's extra boys, and you can have p-type, where there's a missing boy, missing. Okay? And even though these are 2-dimensional representations of what's happening in 3D, the picture does represent very well what is going on. So you have missing electrons, or you have excess of electrons. This would be a N-doped. This would be a p-doped. Okay, now, what does it take to make this stuff work? Well, that's the next chapter. So we're now through chapter 1 without the rest of the story. But we now know that you can do P and N on top of silicon, which is a purest 4, it's a pure 4, and you can go 5 and go 3, and you can get 1 above and 1 below, okay? Now you want to make it so that you have these junctions. And they're talking about what it takes to get through the junction. Now, you can study this for a long time, or you can study just a few minutes, and you can say the same basic thing. How does this ever work? Well, there's a big explanation in which he kind of does a pretty good job of, and I read through it and I said, well, that's nice, but how can you get through this? Well, in a way, you just go to the end and say, no, that's how it works, and then you back up and you say, oh, I kind of see how it works based on that. This is a p-n junction. This is your diode. Okay, right there is nothing more than a diode. That's what that is. That's a diode. It's a p-n junction. Now, this is what a diode's looks like right there, right? That's a symbol for a diode. Now, we define it as current going like that, right? The current is going in the direction of the arrow. That is really not electrons, that is positive current. Which way did the electrons go? The electrons go this way. So they actually flow the other direction. That being said, oh, and by the way, the other day I labeled I'm sorry about the transistor. I labeled this EBC. It's really CBE. That's the right labeling for it. I got it backwards in my. It's been a while, and it really, you have to go back and you have to remember all this stuff, and I do, but it just takes a while sometimes. I made a mistake. All right. Now, there is right in here excess electrons, and this is an excess holes. So the plus means there's excess electrons, and the minus means there's excess holes. Now, up until a certain voltage that you put across this thing, it's going to and this is the way that it works. Okay. At some point, this guy is going to start conducting, but he doesn't conduct at 0 volts. He conducts after you go a little bit above 0 volts. And when does he let loose and start conducting? Well, it has to be after the and it sounds ridiculous, but it's after they've climbed the electron hill. Okay? So you have to put enough voltage across this for there to be a breakdown and the electrons to shoot through from this side to this side. And then they start traveling around this way and they keep going. And once they let go, after you get to a certain voltage, it acts like a short circuit. It acts very much like a dog, and the author talks about this in this chapter. He talks about it like a little door to let your dog out. It's got a spring on it that'll close it back. The door can go open, and the dog can go out, but it can't come back in. So this guy, once the dog is out, it closes back up. But if the dog wants to go out, he can go through the hole. All right? So the dog can go this way, but it can't go this way. It's blocked. That makes sense? You got it. That's a diode. So the spring is the 0.7 volts. That's what it takes to open the door. Once you've opened the door, let the dog out, it'll go. But you can't get back in because it's blocked. That's not true if you put enough voltage on it to overpower everything. If you put enough voltage on this that you blow everything up, at that point in time, what happens? You don't see physical smoke, but it never works again, all right? You'll blow it up internally. This thing will be fried internally. So if you put enough negative voltage on it, if you put enough negative voltage that you go above it, its rated voltage rating. Everything from now on out has a voltage rating. And if you go above that, it's like poof, it don't work no more. Okay? You can do two things to these guys. You can solder them, or you can get them too heated up that they lose their whatever they've got. And the other one is you put enough voltage in a negative direction, they can let their smoke out that way as well. So you got to be careful, and you can also touch them sometimes, and they'll do it. What does that mean? You carry enough static electricity with you that you actually can break them down by just touching them. So that's why they have static pads. That's why they have static, you can stand on something. That's why they have gloves sometimes. And you should always be careful when you're handling semiconductor devices that you don't have too much static electricity on you. So that's another side of it. You can kill these guys a number of ways. You can fry them by putting too much current through them. You can fry them by overheating them. You can fry them by soldering them and getting them too hot. You can fry them by putting static electricity in them. Other than that, they work just great. Anyway, lightning does it too. Lightning lightning does wonders to semiconductor devices. You all know, if you have a house that get a lightning strike, and some of your devices work after that, and some of them don't, and it happens. But this is the way it's supposed to work. Now, this is the side that, if you took this picture, it would look exactly like this, okay? So the positive current is pointing that way, but the negative current of electron flow is doing this. And this is the way the electrons flow. Backwards from the positive. We always draw it the other way, but it's really the opposite. This is because of Ben Franklin. You can blame Ben Franklin for this. He got it backwards. Okay, so that is what it takes. What is the electron hell for silicon? It's 0.7 volts. For germanium, it's 0.3 volts. So why don't we use germanium? There's more silicon out there than there is germanium, by far. Germanium is not easily found, and silicon is what? Sand. Plenty of it. Okay, so that's... Still trying to think of the guy that invented the integrated circuit. Reverse bias, doors closed. And this is an equation for Shockley's equation. I would not use that at all. But this is the way that you can actually describe current in a to a certain point, all about 0.6, 0.7 volts takes off, and it starts up, and it's almost like a 0 ohm resistor. Very, 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 very low. There's a little bit, but it's very small. Here it is on the logarithmic scale. This is the logarithmic scale going in the other way. This is the graph of it based on looking at the forward direction and the reverse direction. So if you put the reverse direction, at some point it goes kaploid. Over here, it just acts like a short circuit. You can get the dog out the door, no problem. Coming back, you can't get in. Over on this reverse side, at some point in time, you can break the door down. And once it's broke down, it don't work no more. Except for one style of diode called a Zener. And in that case, you actually play with this negative side and use it to control output voltages in certain devices. So if you want to have the Zener is the only exception to that, and it will allow you to, across a certain range, to be able to get a voltage that you can use in this back region. But this is not what we're talking about right now. We're not talking about Zeners. We're talking about regular diodes. And once you break it down, you've let the smoke out, and it will not work again. Okay? Now, I'm not a big memorization person, but if you can remember, a lot of people call this the A and the C, the anode and the cathode. So the A is before the C, and it's left or right, anode, cathode. Okay, that's the picture of it. Some people do that, some people do this. There's the picture of it in real life. There's the line, there's the line, there's the line. So the line is on the side of that you saw the picture. Right there, right there, right there. Okay? Easy, easy peasy. Now that's a diode as well. Just a big one. Do they make them big? Yes, they do. Okay, so that kind of gets you through a little bit, chapter 2. Now but now you're getting into the problems, right? Now you're starting to say, now he's starting to ask us and show us things that you can actually ask on a test. And yes, you can. Now it starts. Diode circuit model, a little bit, not a lot, but a little bit. So there's 3 basic models. This one, and this one. This one is the really crude, this one is the not quite so crude, and this one is the, maybe a little bit, but there's no really good reason to put this resistor in there, but they do. Now you say, what's that 0.7 volt doing in there anyway? Usually I can just do this, right? Not always. And a story that you may or may not believe, and I believe it because the guy telling it to me sounded like he thought it was the truth. So people have stories, right? And they always come up with, this sounds plausible. So Monicon built the 484 programmable controller back in the mid to late 70s, 1978. And they put it out the door. And for whatever reason, I bought 2 of them, and I put them in a plant in Huntsville, Alabama, and they worked like a charm. Libby Owens Ford, I had left Libby Owens Ford, and I moved over and then ended up at Owens Corning Fiberglass. But the guy that I knew still from Libby Owens Ford, who was my friend, he bought a bunch of these in 1978 or 1979 or 1980. I don't remember what year it was. But anyway, he bought a bunch of them, and he took them to their plant in Sherman, Texas. So I went to Huntsville, Alabama, and I had good success with them. He went to Sherman, Texas, and had all kinds of problems with them. Now, I do not know for sure what the problems that he had were, but he told me that one of the things that he noticed was that this is the basic problem that he had, and this is the kind of stuff that you will find. This is why they pay you. If you don't understand, you say, I'm learning all this stuff, but I don't understand why I'm going to get paid $70,000 or $80,000 to start, and why I'm going to get paid $120,000 in 5 years, and all that good stuff. I have no clue. This is the kind of stuff that, and why you're taking this course right now is why this kind of stuff happened. Because in his situation, they had robots. These were pick and place robots, and they would occasionally, and they were all being run by these guys right there. And he said that on occasion, not all the time, but on occasion, the robot would start to pick up a piece of glass, and then it would lose its cookies, and it would smash it down, and you would have a smashed whole thing with smashed glass on it. It was a mess, and they had to clean it up, and then they'd go again. And it just happened every once in a while. It didn't happen all the time, it just happened on occasion. So the I/O had a diode pointing out from the main, and he noticed that it was there. And they started at plus 5 volts. So this was a drop of 0.7 volts. So what do you end up with? You end up 4.3 volts, right? Okay. Now, most of the time, this was good enough to do your logic. Every once in a while, there would be a calculation that it would run into that 4.3 volt range. And sometimes when it did that, it would lose its cookies. Now, he said they never admitted it. They never would say anything. But he told them that. And he said, if you up the voltage to 5.7, it might cure the problem. And they did, and it did cure the problem. But the lawsuit, I don't know whatever happened to the lawsuit between the two companies, because this went on and on and on. This was well after the startup of that plant. Okay? But do you follow what I'm saying? You lose 0.7 volts. Sometimes it doesn't matter. Sometimes it does. And that diode in that circuit protected something from something else. We don't know what it did, but it did do something. But it also dropped the voltage down to 4.3. I didn't have any really hard calculations in my program. He did. Like, as you have more complicated calculations, it takes more voltage to do those calculations. And that's what was going on with him. And I believe him. I think that's what it was. I can't prove it, but I think that's what it was. And he said they quietly upped the voltage. They didn't tell anybody, but they upped the voltage, and it never did it again. Anyway, so you think that nothing ever happens on your watch? Think again. It can. Not that you always are out there looking for everything to go wrong, but if it does, this took him months to figure this out. It didn't take days or weeks, it was months of trying to find out what this was. Any questions? Any comments? You say, so now all I'm doing is looking for 0.7 volt drops and they're all bad? No, they aren't all bad. This one was, evidently. Okay. So now you know that you can run into problems. And this is the kind of problems that this is why we talk about the voltage drop of across a diode, because it does take some voltage. That's why this is probably the better, in my opinion, than this. Although most of the time you just think about the dog going in, the dog going out, whatever. Dog going in, right here. Dog going out, dog going out, right here. Dog going back here. You can't go in. Okay. Any questions? Any comments? Please don't put me out there where they have to make me think about all this kind of stuff. This is where you're going to go. Any questions about any of this stuff? So now what do you have to think about? This drops 0.7 volts, so you take this minus 0.7 volts, and that's the voltage across the resistor. Okay? So you see the different model does something differently. So here it is without, this is the answer to the question, the first approximation, this is the answer to the question. If you put the 0.7 volts in, you have to take 12 minus 0.7 volts, and that drops the current. And it does drop the current. You do see that. The third application, you have to add in the R plus the little r of the bulk, which is not a lot, but it's a little bit, and it drops a little bit more. Which one would I use? In the real world, I'd use this one. But you might be asked to use this one. I doubt it, but I just doubt it. Now, what about this one? The dog can't go through. It's blocked. No current flow here. I equals 0. Open circuit. The dog is blocked from going back through the door. End of story. Current can't flow this way. It's gone. 0 current, 0 voltage. Where does the voltage go? It's got to sum to 0 around the loop. All the voltage goes across the diode. It's like an open circuit. It doesn't help you to have, the only thing here is that now you had you have 2 voltage drops. Okay. What about this? Well, it's 0.7 volt across here. So you have 0.7 volt. You have this, And this is 0.7 volt right here, right? So you have 10 minus 0.7 volts, and that's the current through there. Now what's the current through there? 0.7 volt divided by that resistance is the current through there. Does everybody see this stuff? It's not hard, but for the first time when you look at it, it's like, what on earth are they talking about? You got to climb the electron hill. In my earlier days, I would get up and I would actually start climbing. I am old, so I don't do that anymore. I don't climb no electron hills anymore. But that diode does. It's got to climb a 0.7 volt electron hill. It's got to go up 0.7 volts. It's like putting a 0.7 volt supply right across that device right there. And say that's 0.7 volts. So what's the voltage over here? It's got to be 0.7 volts. 0.7 volts, what's the current through it? Bingo, that's it. No big deal, but it's there. Okay, now this is other types of diodes, and we're not going to study all these today, but there are one in here. This is the Zener. This is the one I talked about that actually does that backward. That has it's kind of like you can use it as a special application. Okay. So here is a Zener, and at a certain voltage, it does allow reverse. Okay, so at a certain voltage, it does turn on. In other words, it allows you to go through. It takes out certain voltages, and at a certain point, it does allow you. And you can get current after that point. So this one is rated at 5.1 volts, so it will, in the reverse direction, it will turn on if you go above 5.1. And if it's above 5.1, it will conduct, but only conduct above 5.1. That's a Zener. An LED, just like a regular diode, except for the fact that you got little arrows flowing out from it, which give you current or give you light. There they are. They work in one direction. If an LED is turned around, will it turn on? It will not. If it's reverse biased, it will not turn on. It's got to be forward biased. And you have to put a resistor in series with it or it will burn up. Two things about LEDs. You can turn them around and they won't work. And if you put them in a forward direction, you put a voltage across them, they might burn up. So you have to put a resistor in series with them. Okay, now LED lights that you buy have already put the resistor in series and they're already enclosed, but you don't have to do that. But if you build the circuit yourself and use an LED, which is one of those guys, then you do have to do that. And their LEDs are very interesting devices because they look like, you look at them, they've got a flat side, okay? And this is the same as the side that is like this. This flat side is that side right there. So they've got two leads, one here, one here, and one here, and this is the side that goes that way, and this is the one that goes that way. So basically, and there's a long and a short one. I forget which one is which, but the flat side is the downstream side. So that's how you do LEDs, and you will have to do that in your all right, enough on that. Any questions so far? I know I'm going through a bunch of stuff in a hurry, but I want you to be able to get to something that actually is real and Shockley and varactor diodes. Don't use those at all. Yeah, I'll come up with a couple problems that we need to work out of this chapter, but I do want to, this is chapter 2. So we're going through these chapters very quickly now, but we will come up and we will start working problems. I'm not going to work them today, but we will come up with some some assignments from these chapters that you have to hand in, and I'll put those on the website and I'll get those taken care of. I have not updated your webpage yet or your syllabus yet, but I will. I'm planning on doing that either today or tomorrow. I'll get that taken care of. So the only other thing I want to talk to you about, some of you have come in since I first did my little show on what's up in those boxes up there. And what is in those boxes? It is a, show them to you. Sign in. Okay, so I'll show you what we have here, and you probably don't know what I've got up here. I'll show it to you. So I knew we were going to run out of relays, and these boxes up here in the front are relays, and they're packaged kind of differently than what you have up until now. But these are the relays that are really thin, and they're cheap, and you can look at these and build up based on that. And there's enough there there's 60 relays, and you can have 3 or 4 or 5 of these. You can either put them on your DIN rail, or they can go on this DIN rail that they've provided. And there's jumpers if you need jumpers. There's some jumpers in there. End plates if you need end plates. And there are 60 relays. There's 10 relays per box, and there's 6 boxes. So don't take them all. Take a few if you need them. And if you need 3 or 4, if you need 5, that's good. I bought enough so that everybody had plenty. This time I think I've got enough. So you've surprised me, and it's a good thing. I appreciate everybody getting involved in this, and I will help you. I'll come up there even today if you want to. If you need anything, you can either text me, or I'll just come up there for a little while. I'll take these up. Once I go back to my office, I'll take those up and put them on that cart. So you'll have them on that cart. I took one of the boxes and looked in it and saw what was in it, and I've not disturbed any of the other boxes. So you can have half of a box. I would say half of a box maximum, okay? But you can take those and you can split them up however you want to. And I'm still trying to remember the guy that did the integrated circuit. I will have it next time. Anyway, so you can brag about the University of Toledo. There's a lot of good people that have gone through here. Guy by the name of Liddell, David Liddell, was one of the co-inventors of the mouse. Yes, the MOUSE that we use. He was one of the co-inventors of the mouse. A guy that I know, a very good friend of mine, Nate Holt, invented AutoCAD Electric. So if you ever deal with AutoCAD and you deal with the electrical package on AutoCAD, Nate Holt wrote that from scratch by himself. And he's still alive, and he's still in Toledo, Ohio. He lives out in a suburb of Toledo, lives in a Sylvania Township, but he's a native of Gibsonburg, and went to the University of Toledo, graduated with a bachelor's in electrical engineering, and went to work for Owens Corning Fiberglass. So anyway, there's some good people out there, and they've done some really interesting things. The guy that I talk about from engineering technology is Tab Fischbach, and he didn't invent anything, but they made the interface between Amazon and UPS, his company, and he was the head of that. He was the president and owner of that company, and I guarantee he had his finger in every part of the engineering of it. He's an excellent engineer. So if you want to know what you can do from here, you name it. So anyway, but you got to understand some of this stuff first. You can't just go out there and say, let me at it. You got to understand some of this stuff. And that's where you're at today, is getting started in a new area, new subject, trying to transition from that other subject, Bodie plots and all that kind of stuff, and trying to grapple with that, and then come to this other subject and trying to say, now, what's in it? And then also trying to do this project. And you also owe me that conduit layout. And what else do you owe me? Some problems from chapter 10, which is not chapter 10, it's those 8 from that separate thing. What else do you owe me? You owe me something else. That's about it, right? What else do you owe me? Anything else? That's it, right? That's about it. And then we start another book. So there's a lot going on, and we still have a little bit of time left. Don't give up. Don't sit back and say, no, he's going to cruise the rest of the way. We're not going to do anything. Well, that was last year. We did stuff, but we didn't start in the next book. We never made it to this book. I had every intention last year of getting into this, and we just kind of stopped. So now we're going to work on the project, and everybody kind of tap danced their way through the last month of April, and that was it. This year, we're not going to do that. We're going to continue on. We're going to work on those projects. And if you get stuck on that project, I can help you, but I'm not going to just go in there and build it for you. You're going to have to build it yourself. End of story. Take care. I want to shut this off. And does anybody have any questions?